In this lab, we will be discussing an application of Newton's second law, when the net force of an object is zero, or in other words, when there is constant velocity.
An object moving at constant velocity has a consistent position versus time ratio. This means that the slope of the position versus time graph is constant. In order for velocity to be constant, the net force must be zero. When we apply this to Newton's second law, we see that the final velocity depends only on the initial velocity. We can make the mass anything because the net force is zero. For my experiment, I decided to roll a volleyball across a flat surface. Upon analyzing the video with Tracker, I decided to crop my video in order to focus on the constant velocity portion of the motion. Therefore, the video begins at frame 37 and ends at frame 81. There were some parameters I had to take into account when tracking my video. The first was the diameter of the volleyball, which is 0.21 meters. I calculated this by using the circumference of the ball itself, and I adjusted for it by using the calibration tool in Tracker. The axes were set using the coordinate axes tool in Tracker. The axes were established in frame 37, or at the start of the motion track video, using the center of the volleyball, as you can see here. The center of the volleyball represents the center of mass and was used to track the motion of the volleyball as it progressed across the positive x-axis. The ball's initial position was 0.002 meters, the ball's final position was 1.093 meters, and the observation start and end times were 0.00 seconds and 1.72 seconds respectively. In order to calculate the ball's initial velocity, we used the following equation. Entering the corresponding information from the time versus position table from Tracker, I calculated the initial velocity to be 0.75 meters per second. In my experiment, the volleyball was moving from left to right, so I decided to set the axes using the positive x-axis. This resulted in a positive x component and a graph sloped upwards, creating a positive velocity. However, if the ball had been moving from the right to the left, or if I had set up my axes using the negative x-axis, my x component would have been negative, the graph would have sloped downward, and as a result, the velocity vector would have been negative. In order to recreate the motion of my experiment using the PHYS program, there were parts of the code that needed to be updated with the information specific to my experiment. The volleyball's mass is accounted for in the ball.m variable by setting it to 0.27 kilograms. The ball's initial position and velocity are updated appropriately using the data explained before. We leave time t equals 0 because the initial observation time is 0 seconds. Because the video is only 1.72 seconds long, we want the delta t to be very small in relation so as to give the most accurate calculation of velocity as possible. The while loop is updated to only work while the time is less than 1.72 seconds, which is how long my video is. We set the variable fnet to 0, the vector, because we are dealing with the motion in constant velocity, which means there is no net force acting on the object. We update the variables ball.vel and ball.pos to reflect Newton's second law. It is important to note that just because the net force is 0, that does not mean there aren't any pushes or pulls acting on the system. In fact, there could be many pushes and pulls acting on the ball, such as friction between the volleyball and the table or drag force. When calculating the pushes and pulls that affect the net force, we must be careful to count all forces acting on the system from the surroundings, to not count any forces acting on the surroundings, only the system, and to remember that objects do not exert forces on themselves. Here is an animated representation of my experiment using this code. From the data gathered from both the expected velocity from PHYS calculations and the experimental velocity from the table and Tracker, I created a table that shows the difference between the predicted and actual velocities of the volleyball. As you can see from the graph, both the experimental and predicted velocity lines have a constant slope, which is consistent with the idea that the volleyball was moving at a constant velocity. However, we can see that as time increases, there becomes a discrepancy between the experimental position and the predicted position. This could be the result of a number of things. 1. While tracking the ball in Tracker, some human errors could have occurred in locating the center of the ball, which would have affected the position of the ball. 2. The ball could have started to slow down towards the end of the video. In order to fix this, I could have made the end frame sooner in the video. And 3, if there was any motion in the z-axis, in other words, if the ball moved from the middle of the table to the back of the table while filming, that could have affected the tracking position of the volleyball.